This is the third video I've just taped in a row, so just call me Butter, because I'm on a roll. You guys have said I've made these too boring, so I'll try to jazz it up. Besides, I'm getting a little bored. I'm sitting in my classroom with no students, and there's nobody to talk to. Anyway, we are on Lesson 6.6, Use Proportionality Theorems. This can be found in your book on page 397, but on your vocab sheets that I've said over and over again, it's worth 40 points, need to be complete in each section. Can you take a minute to read and interpret Theorem 6.5 and 6.4 and do a sketch, state the properties that you know to be true, and put it into your own words. And I know sometimes with a sketch, for me it's important to put numbers in there as a realistic example, but go ahead and pause the video and get your vocab sheet turned out or filled in. Okay, then we go to our first problem. First thing I'd like you to look at is this problem. In the diagram, QS is parallel to UT as it's marked, so that is the given. If it's given that it's parallel, we know that those parallel lines can intersect or cut the triangle into proportional triangles, or a proportional relationship, or into similar triangles. So this little triangle is similar to the bigger triangle. So the stuff that's marked is there, and we want the length of QU, so that's your X. So essentially you can set up a proportion. 12 is to 6 as 10 is to X. And you know that with your proportionality rules you could have done a lot of different forms of this. 10 is to 12 as X is to 6 would have been acceptable. X is to 12 as 6 is, and so forth. A lot of people ask about that one theorem for proportionality that we didn't really like a whole lot. The one that looked like you could add the denominator to the bottom or whatever. Here's one way that you could do that. You could say you could say this small part is to the whole part, which the whole part would be X plus 10, as this small part, is to the whole part, which is 12 plus 6. Okay, now I'm guessing that in this instance that's not the choice that many of you would use, but you see how this is really an application of that one proportionality theorem where you can add the denominator to both sides of a proportion and it will be congruent. So in this case it's the entire length over the small part is equal to the entire length over the small part. Okay, so go ahead and solve that proportion, and this is one answer that I will be checking first thing tomorrow. Okay, the next application problem I would like you to look at looks like this. Find the length of YZ. Okay, so YZ is right here. Notice this is the application of 6.4 because the given is that they're parallel. Okay, so set up the proportion to solve. Now the next, you'll have to pause that if you'd like. The next one is, if you're given the parts, can you determine if they're parallel? So that's the converse. The converse says if they're parallel, it divides the sides proportionally. The converse is if the sides are divided proportionally, then the lines are parallel. So we need to decide, is this divided proportionally? And it looks like that's 90 and 50, 72 is to 40. So you could do something like this. 90 is to 72 as 50 is to 40, and try to determine, are those equal? You could do lots of different proportional forms. but you should be able to find that and be ready to explain that tomorrow. Okay, the last one that I'd like you to do, or I'd like you to look at, is if you could turn in your books to page 398. On the back of your vocab sheet, where you just got done doing 6.4 and 6.5, I'd like you to take a minute to write in, make a sketch, an explanation for 6.6 and 6.7. This is on page 398. So pause the video and get those two things taken care of. Okay, so there's lots of different applications of this that we're going to look at, but the first one we're going to check out is this one. And it says, in the diagram, QPR is congruent to RPS. So whenever you have a given statement, so that's your given, you need to think to yourself, what is this telling us? Well, if this angle and this angle are congruent, doesn't that mean that PR is an angle bisector? So that's going to be working with theorem 6.7, which says if a ray bisects an angle of a triangle, then it divides the opposite sides into segments whose lengths are proportional to the lengths of the other two sides. So what that means is that this side is to 1 as this side is to 13. Alright, but we can't call this x. This part is called x. The whole thing is 15, so isn't this part right here 15 minus x? Okay, if that doesn't make sense to you, pause it and kind of listen carefully to what I said there. So we're going to set up a proportion. 1 is to 15 minus x as 13 is to x. Okay, so as we cross products x, we do 13 times 15 minus x, and we get, oh, I'm sorry, this should be a 7. Okay, so we're going to change this. This should be a 7. So this is 7x. So it's 7x equals 195 minus 13x. Okay, you can solve this in lots of different ways. Add 13x to both sides and divide by 20. So x comes out to be 9.75. Okay, if you want to check to see if you're correct, if you put 9.75 in here, you should be able to see, work those out and see that those are stay in the same proportion. Okay? Alright, that's it for today's work. Hopefully you're keeping up on your note cards, your note vocab sheets, and you're good to go. I'm out.